Timer? We need all the time we can get here.
Does it say like 3 after 11 on your clock out
It
there?
says 1:11.
I mean the time is like 3 after 11, right?
Yeah, 2. 2 after 11, roughly. Okay, we ready to go? All clocks synchronized. All right, to begin with, are there any questions? I was thinking about this, and recently, it seemed to me that recently people haven't been asking very many questions. So I don't know whether that means because things are getting clearer and clearer, or the reverse. So, everything going okay? How about the Port St. Lucie crew? They haven't asked any questions either. Any questions from Port St. Lucie?
We're doing okay so far.
They can't hear me.
So she's doing
We're
okay.
Doing okay, okay. Everybody else doing okay? Any questions? I guess that means yes, right? All right, so the last thing we were talking about was expected values, and in fact I had started talking about the application of this to the birthday problem, which was homework 2, which I'll finish talking about. I'll start again today, and let's make that due in a week. So it'll be due next Thursday. It's actually very easy. It'll take you just a couple of minutes. So we're talking about expected values. An expected value of a random variable x, that's the mathematical model of the notion of average. And we have two formulas. In case the random variable is discrete, what you do is you take the values the random variable takes, which I call T1, T2, and so forth. I multiply or weight the values by the probability that the random variable takes that value, and then I sum it over all possible values. So that's it's the center of mass. That's the expected value. It's sort of like a summary single statistic that represents the whole distribution. If the random variable is continuous, then of course it doesn't have a probability mass function, but it has a probability density function. So the analogous formula would be this. Instead of the probability that x is equal to t, you would write the density function evaluated at t dt. So you interpret this as the probability that x equals t. You multiply that frequency or that probability by the value t, and then you sum that over all values of t. Those are the formulas. And I gave some examples of those. And in particular, then, we wanted to look at homework 2, which is the birthday problem. So here's homework 2, which is the birthday problem continued. The birthday problem began with homework 1. In homework 1, what you did was you simulated it. What you simulated, and it's important to understand, go back now and understand what your simulation is, because now this is going to describe, or I guess describe is the right word, the rest of the course. In the sense of what we're going to do now is develop this theory and then compare the theory with experiment. The experiment is simulation. So the computer conducts an experiment that is which the theory presumably is describing, and then you compare the two, and of course, if everything works out, they agree. So you've already done the simulation part here, so now we want to do the theory. In other words, I want to apply this formula right here. And the question is that you're questioning people one at a time and asking them for their birthdays. And you do that until for the first time you get a match. That is, someone's birthday matches the birthday of someone questioned earlier. And the random variable x is the number of people you question until you get that first match. So it's going to be a number between 2, the smallest possible value. 2 is the first possible time for a match is when you question the second person whose birthday might match the first. And the largest possible value was 366. That is, if the first 365 people all have different birthdays, then the 366th person must match one of them. And the question is, on average, how many people do you question? And as you know from your simulation, the answer turned out to be about 24 and a half, which most people found surprising. And so now we're going to show that that's actually what you would get when you calculate it. So the calculation went something like this. We said that the expected value of x, in this case, would be the sum. Now, the values of the t's, the values of the variable can take are the integers, which I'll call j, and j is going to run between 2 and 366. We have to multiply that, each value the random variable takes, by the probability that it takes that value, the probability mass function, and add those guys up. And so all we have to do is actually write out what these probabilities are, plug them in the formula. There's too many of them to do by hand. You have to write a program to do it. So I did some of this before. What's the probability that x equals 2? That is, that the first match occurs on the second person. And you could write it like this. It could be written as 365 over 365 times 1 over 365. The reason why I wrote it in that form will be clear soon, but you can see that the probability is 1 over 365 because whatever birthday the first person has, there's one chance that at 365, the second person's birthday is exactly the same thing. Okay, so the probability x equals 2, and then you can easily see that the probabilities look like this. For x equals 3, it would be 365 over 365, that corresponds to the first person's birthday, and then 364 over 365. So this value 1 is the probability that the first person's birthday does not match anybody previous, which of course is 1. And then this is the conditional probability that if the first person's birthday didn't match anyone, the second person's birthday will not match the first. So multiplying these out is the probability that the first two birthdays are different, and then we want the third birthday to match, so the conditional probability of that, if the first two are different, is now 2 over 365. So you can continue this reasoning. You can see what the pattern is. In fact, you can now write these things out without even knowing what it is you're doing. Just copy down the pattern. So this probability x equals 4, 365 over 365, 364 over 365, 363 over 365, and then 3 over 365, and so on. So in fact, I could write, in general, the probability that x equals j. So that's going to look something like this. The first term is going to be 365 over 365. Then you can have a bunch of terms like that. And so the last one, next to last one, would be 365 minus j plus 2 divided by 365. And then the last one is j minus 1 over 365. So you can see that if you plugged in j equals 4, for example, this would be exactly the same as that. Now, when you're doing that, you'll note that the number of terms here is exactly j minus 1. But you don't want to calculate the probabilities directly from this formula because depending on how you do it, you could run into accuracy problems. Because, for example, when I multiply out the denominator, 365 times 365 and so forth, if I multiply 365 multiplied by itself j times, and j is going to run between 2 and go as high as 366, the denominator can be enormous. And of course what will happen is as j gets bigger, the numerator is going to be smaller and smaller relative to the denominator, and the probability in fact is going to get very tiny, but the numerator and denominator are going to be gigantic numbers. So you could run into problems if you just calculate these things directly. So you're supposed to use the knowledge that you all gained by taking a course in analysis of algorithms or something like that. So the way to do this then is to rewrite it as follows. What I'm going to do is I'm going to represent the right-hand side in terms of the probability that x is equal to j minus 1, because you can see it's almost the same, so it's easy to check the following. Here, I'll write it here. So, the probability at x equals j is the same thing as the probability that x equals j minus 1 times 365 minus j plus 2 divided by 365 times j minus 1 over j minus 2. In other words, if you look at this thing right here and write out that term there, then you'll see that when I write out this term, that to go to the next one, all I do is add on one more term. Okay, that's in this case this one, then this one, and so on. This is the last one. And then I have to take the final term and change it from, in this case, 1 over 365 first to 2 over 365. Then change that from 2 to 3, change that from 3 to 4, and so forth. So I get that by simply multiplying this result by j minus 1 over j minus 2. So if you plug in this formula with j replaced by j minus 1, right here you will see that you get exactly this formula back again. So this is the iterative or recursive way of looking at things, which of course all computer scientists are supposed to appreciate, and which is especially important in probability, because lots of probability problems have this structure. You can represent the probability for some number of trials in terms of the probability for the preceding number of trials. So anyhow, just simplifying this, this becomes probability x equals j minus 1 times, and then I'm just going to combine those two terms. So this term is 367 minus j, that's that numerator, and then I have a j minus 1, that's that guy, and the denominator is 365 times j minus 2. So I combine these two terms to that. So this is my formula, and all I have to do is specify the boundary conditions. So they are that j is going to take the values 3, 4, and so forth up to 366. And at the starting value, the probability that x equals 2 is equal to 1 over 365. So what you have to do is you have to write a program that implements this algorithm. So you can do that in just a few instructions, even in BASIC. It's really simple. When you do that, you get the answer. And so what you're supposed to do is write the program, hand in the code, the output, and on the cover sheet, write the numerical answer that results. And then look at that answer and compare it with what you got when you ran the simulation, and you'll see that it's almost exactly the same thing. Of course, this is exactly theoretically correct, and what you got with the simulation is a little bit off because the simulation is only an approximation in several different places. And we'll get to that later, why it's only an approximation. Okay, so that's all straightforward, and so let's make this due on Thursday. If you have problems with it, you can ask about it in class on Tuesday.
Next Thursday?
Next Thursday, right a week.
Question
Should
in
take 5
what's it
minutes.
listed? We have a
There's
question
a
over
couple of
here.
common errors that are made.
She has a question.
Question, okay. My day is much better. Yes, what's the question?
It's you have the probability that x equals j minus 1. I don't know.
So this is actually a course in communications theory with a channel and noise. Delay in the channel, I guess.
If I talk
Maybe
louder,
that's
can you hear a little
information
better?
theory and error correcting codes.
Oh. The probability that x equals j minus 1, what
I'll get
is
somebody to try to
that?
fix the volume.
Okay. So it's a volume problem. Okay, while you're fixing the volume, a couple of errors here. Remember that when you calculate this expected value, don't forget to multiply by the value j. So a common error is for people just to put the probabilities in here. If you leave the j out, what does the answer come out to be? come out to be 1, because if you sum all the probabilities over every possible case, they have to add up to 1. So a common error, I see it immediately, is for people to write down the answer 1. So if you see that, you know what you forgot to do. And the second common error, there are versions of this, is to start with 1 instead of 2, or end at 365 or something like that. In other words, get the limits of the loop wrong, or get these out of sync. Some people take this to be j and that j minus 1 or something like that. Those are just programming errors. Okay, we got the volume problem fixed? I guess not. Oh,
I guess you
okay.
could ask her to ask again.
Okay. Okay, can you ask again?
Yeah, on the final equation that you gave us for probability x equals j, you have probability that x equals j minus 1 on the left board at the bottom.
Yeah.
Yeah, we were wondering what that is there. Are we just recursively doing the second part of that
Yes.
equation?
Yes, except it's not really recursive, it's iterative. That is, what you do here is you set j equal to 3, and that means this would be the probability x equals 2, which is 1 over 365. You plug in the value of j equals 3 here, you multiply them out, and what you would have is the probability that x equals 3. Then to calculate the probability x equals 4, you would take the previous calculated value, which is now j minus 1, that would now be 3. You plug the value you just calculated in here, plug in j equals 4 here, do the multiplication, and the value is the probability that x equals 4. And you just keep on doing that. That is, you calculate the right-hand side, and then for the next step, you take the value you got, you put it in here, multiply by that, and calculate the right-hand side again. And so you keep on doing that until j is finally equal to 366, and then you quit. And as you're doing it, remember that every time you get a probability, you have to multiply it by the value of j and accumulate them, and then what you print out at the answer is the cumulative sum. That answer it?
Yes, thank you.
Okay. Do you have a question?
Yeah, it was just pretty much the same thing.
Same question? So I should probably give the same answer, right?
Yeah, but when I plug in 4 there, probability x equals 3. 4 minus 1 would be 3, right?
Right.
So what I did was took the value of p x equals 3 from the other one, where
Right.
I calculated it.
From here.
Yeah.
Except that,
Can I do that?
well, you don't want to calculate it from here. The whole point is that you're going to calculate the probabilities from these formulas only one time, namely this time. And then after that, the thing you put in here is what was calculated from this formula. So that you put this in a loop, which simply, every time you go through the loop, you take the value that you computed the previous time, you multiply it by that, and then you replace the probability, that value, by what you just got. And you simply do that over and over again. It'll take like a millisecond. I mean, it goes like instantly. And you don't want to do it recursively in a sense. You don't want to build up a stack and unwind it. That could take forever.
So just get the first value and then store it in the variable
Right.
on the left-hand side, and then loop it around.
Right, you put it in a
Just
loop.
store the value into that.
That's right.
In the other one.
Right. Just put it in a loop. In BASIC, it's like that many instructions. In C or C++, it takes a little bit more space, I think, because you have some overhead, but the actual calculation is even
It
shorter.
would just be one statement. Instead
Yeah,
of
that's right. Right. It's trivial. Okay, but I'm trying to make a couple of points here. One is probability. You often use these kinds of iterative calculations. The second is, this is a review of the earlier part of the course, because that's what you needed in order to write these probabilities here. The third is that it's an example of an expected value. The fourth is that it compares the expected value with the average, because that's what you got in homework 1, and you see that they are in fact approximately the same, and they are what most people find surprising, at least at the time, which is that the value is so small.
So the expected value would be equal to the value what we got when we simulated it.
When you did homework 1, most people got a value of 24.38 or something like that. That's not the exact answer, that's the simulation answer, which is an approximation. But the answer will turn out to be between 24 and 25. And I think just about everybody's simulation turned out to be a number roughly 24 and a half. Okay on this? Okay, so now I want to go to the next topic, which is called variance. Okay, so let me erase this. So expected value is section 4.3. And now I want to go to section 4.4, which is called variance. Now the expected value is intuitively straightforward, but the variance is at first a little bit more complicated. Maybe not complicated, but a little bit more unintuitive. You don't know why you're doing it. So first of all, we're going to define the variance. It's called VAR, which stands for variance of X, or sometimes abbreviated V of X. I like to use the abbreviation, it's shorter. And the definition is this. The variance of X is equal to. Now, what variance is supposed to model or represent is the idea that when you have a distribution of values, that is, in the discrete case, a probability mass function, the values can spread out all over the place. And so you can have a random variable, two random variables that have the same expected value or the same mean value, but nevertheless have distributions that are quite different. For example, I could take a case of a random variable that always equals 50, a constant, that's a special case. So the average of a random variable that always equals 50, of course, is 50. Then I could look at a random variable that takes the value 1 with probability 1/2 and takes the value 99 with probability 1/2. So its average would also be 50, but nevertheless they would be completely different because one of them would bounce around between 1 and 99 and the other one would always give you 50, but they give you the same average. So if you're trying to summarize the information in a probability mass function or in a density function, if you have only one single value to summarize things, probably the expected value is the best single one. But you can get a lot more information if you summarize it in terms of two. One gives you this central location, and the other one tells you how much bouncing around or variability there is in the how much randomness there is in that around that central location. Okay, so that's called the variance, and it's defined this way. It's the average value or expected value of. And then what I want to take the expected value of is the square of the difference between the random variable and its average value. It looks simpler if I write it another way. I'll write that as the expected value of x minus mu quantity squared. So the mu here, this is simply notation. So people often call the expected value mu. I think that's a Greek M, mu. So it looks like a U with a little tail on it. And it's a mu, that's the way you say it. I don't know. I'm always confused about the idea of spelling a letter. How do you spell a letter? But in any event, probably what it stands for is a Greek M, which stands for mean. That's probably why they use that. In any event, people often use that. And so that emphasizes the fact that this thing is actually a constant. Whatever it is when you get it, it's a constant. So this makes it look more like some kind of function. So if you write it this way, replace e of x by mu, then this says that the variance is the average value of the square of the difference between the values the random variable takes and its expected value. So I got to be able to calculate that, but first just look at the definition. Notice that it's squared. So what the effect of that is that it's only the absolute value of the thing in parentheses that matters. It doesn't. The sign, in a sense, is irrelevant. So you only care about how much x differs from its average, and not whether it's bigger or smaller. And there could be other measures, but this one is a simple one, and it'll turn out, later in the course we'll see, to be very fundamental. So it's not an arbitrary definition. All right, so the first thing is, how do you calculate it? Of course, you may say at the moment, who cares how you calculate it, because you don't even know what it is. But we'll get that. But first, how do you calculate it? So to do that, there's a theorem. And so let's see where I am now. Okay, this is on page 161. And here is my theorem 1.3, which is on page 164. Theorem 1.3, page 164. And on page 161, the author is still talking about discrete probabilities, but this definition works in both cases, in all cases. So in fact, if I were to write it out, I would get this. The variance is equal to, so let me write out the two cases. I haven't gotten the theorem yet, I'm just rewriting this thing right here. So I want the expected value of x minus mu squared. So that means that the values that the random variable takes now, that is the value of the random variable whose expected value I'm computing, is t. The t represents the x's, but it's discrete at first, so let's call it t sub I minus mu squared times the probability that x is equal to t sub I summed over all I. So this formula is exactly this definition in the case in which the x is discrete, because it's the average value of the stuff in parentheses. So the average value, take the values the random variable takes, subtract the mu, square it, and weight those values by the probability that the random variable takes those values. If the random variable is continuous, then the analog would be this. Instead of t sub I, I'll just write t. I still have a mu, which is the expected value. I still have a square. In place of the probability that x equals t sub I write the probability that x equals t, which of course is the density function at t dt. And then I integrate over all t instead of summing over all I. And so those are my formulas. Okay, now what the theorem says is that there's an easier way to calculate this than from the definition. So let me go through that. And I'll actually derive it, the theorem, for the continuous case, which is actually easier instead of the discrete case. But it's the same thing. Okay, so let me go through the continuous case. So all I'm going to do is expand this. So when I expand this, I have the integral over t. This means as t varies, that t, between minus and plus infinity. Now when I square this thing, expand it, I'm going to get t squared plus mu squared minus 2 mu t. Density function evaluated at t dt. And now I'll just break this up into its parts, its component parts. So I have the integral over t of t squared density function evaluated at t dt. That's this piece, plus integral over t of mu squared density function evaluated at t dt. That's a plus sign. It's supposed to be. Minus integral over t of 2 mu t density function at t dt. So all I did was expand this stuff. Okay, now what do I have here? Notice that this thing is in fact the expected value of the square of the random variable, called the second moment. Because instead of taking t multiplying by density function dt and integrating, I'm taking t squared multiplying by density function times dt and integrating. So instead of being the average value of the random variable, it's the average value of the square of the random variable. So this is the so-called second moment. We saw this in homework 0. Okay, now what's the next part? Well, the mu is a constant, so I can take that outside. So there's mu squared. And I have left the integral of density function dt over all t. So what's that? 1. I integrate the density function over all possible values, then I get 1. Just like if I sum the probability mass function over all possible values, I get 1. So the remaining integral, I'll write it. Integral t, density function evaluated t dt, and that whole thing is 1. And what do I have over here? Well, let's see, I'll take out the 2 mu, because that's constant. And what's left is the integral over t of t, density function at t dt. But that integral, of course, is just the expected value, or mu. Okay, so where I am is I have the expected value of the square of the random variable plus mu squared minus 2 mu squared. There's the minus 2 mu, there's the mu that's the integral. So that's equal to the expected value of x squared minus mu squared. Or, that's the expected value of the square of the random variable minus the square of the expected value. So the theorem says that the variance is given by this formula right here, which is easier to compute than this formula. So the variance is the average of the square minus the square of the average. Or it's a second moment minus the first moment squared. Now, that's what the theorem says. Okay, so this is theorem right here. The theorem says that the variance is given by this formula. And this theorem is in the book. As I say, it's on page 164. Except in the book, the author does it for the discrete case, but it's the same thing, except that instead of expanding an integral, he expands a sum. But then you do the same thing, identify the terms exactly the same way, and you reach exactly the same conclusion. Okay, so the variance then is given by the expected value of the square minus the square of the expected value. But this statement here, that's a theorem, whereas this is the definition. So I define it this way. This tells me what the meaning is. It's the square, it's the average of the square of the deviation of the random variable from its mean. And it's equal to, computed by taking the average of the square and subtracting the square of the average. So now you could do lots of examples of that. So I'll do a couple. Same old example. So any question there? Okay, so the first example, x equals a fair die. So what I want to calculate is the expected value of the square, because we already know that for this case, the expected value of x was equal to, let's see, what was it? It was 7/2, 3.5. We already got that as a previous example. All right, so the expected value of the square is, from this formula now, would be the sum of the square of the values the random variable takes. Since it takes the integers from 1 to 6, that would be j squared, as j runs from 1 to 6, times the probability that x equals j, which of course is 1/6. So in other words, what I have here is 1 squared plus 2 squared, and so forth, up to 6 squared divided by 6. And that turns out to be equal to 91/6. So that's just arithmetic. So the variance, therefore, is equal to the second moment, which is 91 over 6, minus the square of the first moment, so it's going to be minus 7 over 2 squared, and that turns out to be equal to 35 over 12. So at the moment this is just a number, it doesn't mean anything, but it's a measure of how variable this random variable is. And in fact, this is in the book. This is example 4.24, which is on page 165. Okay? Okay, so let's do example 2. Obvious what this is going to be. Example 2 will be x equals the sum, or the roll, value of a roll, of 2 fair dice. So the expected value of the square of x would be equal to the sum as j runs from 2 to 12 of j squared times the probability x equals j. Okay, that's just plugging into this formula, same formula here, except instead of running from 1 to 6 now, the values run from 2 to 12, and the probability is not 1/6 now, but they're 1/36, then 2/36, then 3/36, and so on. So in other words, if I write this out, this is equal to 2 squared times 1 over 36, that's the first term, plus 3 squared times 2 over 36, that's the second term, and so on. The last term is 12 squared times 1 over 36. Then I just do this arithmetic, and whatever it turns out to be doesn't make any difference, it's just some number. Because we know now that the square of the expected value, that would be equal to 7 squared. Okay, this is the second moment computed from the formula. Now, in an earlier example, we computed and we saw that the expected value of the sum of 2 dice was 7, so the square of the expected value of the sum of 2 dice is 7 squared. So therefore, the variance is equal to the second moment, whatever this turned out to be when you do this arithmetic, minus the first moment squared, that is, minus that, and that turns out to be equal to 35 over 6. Okay, so let me write here after arithmetic, so you indicates that you had to actually do some stuff with your calculator. This is all simple arithmetic. So the answer is 35 over 6. Now, the variance of a single die was 35 over 12. The variance of the sum, which is the variance of x1 plus x2, where x1 is the first die and x2 is the second die, is 35 over 6, which is twice as large. In other words, we observe that the variance of the sum, I'll write it here. So for this example, our observation is the variance of the sum, that's die number 1 plus die number 2, is equal to the sum of the variances. Because in our example, what we showed was that the variance of the sum was, right here, variance of the sum was 35 over 6. And the sum of the variances was 35 over 12 plus 35 over 12. So now we have the same question we had before when we were talking about expected values. Is this a coincidence, or is there some theorem here? And obviously the answer is there's some theorem, namely that when I add random variables, the expected value of the sum is the sum of the expected values. The variance of the sum is the sum of the variances. It's difficult to prove, but it's certainly believable. And so let me write down the theorem. Okay, I want to make sure let's see, it's in the book here someplace. Here we are. So I think I'll write it here. So this is, actually it's statement 9.8, which is on the bottom of page 387. So the trouble is that in order to get to be able to prove this, you got to go through a lot of theory. So that's why we're jumping from page 160-something to page 387, even though we're talking about obviously the same thing. And the reason being is that in order to calculate the variance of a sum, I have to be able to add up random variables, which means take a convolution, and then I have to be able to apply the variance to that resulting density function, and I have to show that no matter what the random variables are involved, if I calculate the left-hand side, the right-hand side, it'll turn out to be the same thing. So it's difficult to prove in general, but it's not a strange result. So here's the theorem. The theorem says this. Theorem. If x1 and x2 are independent, then the variance of x1 plus x2 is equal to the variance of x1 plus the variance of x2. Now, one observation is we don't need only two variables, of course. It works for a sum of variables. It doesn't matter how many of them there are. The variance of a sum is the sum of the variances if the random variables involved are independent. If they are not independent, then this may not be true. It might be, but it might not be. In other words, it's the fact that in order for this to be true, independence is sufficient, but it's not necessary. Now, this is different. So let me go back over here. I'm always running out of space. Okay. So we know also, because we've already stated this, and this makes perfect sense, because this is, well, you don't know what variance is, so it's not unreasonable that it should have a certain property. But we showed also, or we said, that the expected value of the sum is the sum of the expected values. That was intuitively obvious. But the important point here is that this is true whether independent or not. In other words, this statement is always true. This is true if the random variables are independent. So it's a common mistake for people to say that if the random variables are independent, this is true. Well, yeah, but it's also true if they're not independent. So that's an important point. Okay, so let's do a couple more examples. Any question here? This stuff is all kind of dry at the moment because it doesn't get interesting until you're actually applying it to reality, and then sometimes often showing that the reality is not what you thought it was. And understanding, of course, what it means. You always have the problem that first you got to define things and do some arithmetic. You have to take it on faith that you care about what the answer is. And then later you find out whether you care or not. Hopefully you do. Okay, so here's a question. Here's an example. Suppose that x equals a constant. I'll call it c. Now, everything you've done in your life up to this point is actually this case, because you can take the viewpoint that every number you see is a random variable, and the things that you've handled in the past are the special case of random variables that don't vary. So suppose that we take a bigger picture and we say that we have this experiment, but when we perform the experiment, then we always get the same answer, C. It's a constant. So what is the expected value of x? Well, first of all, what's the probability mass function? This is obviously a discrete random variable that takes one value. So if it's a constant, the probability that it takes that value is 1, and the probability that it takes any other value is 0. Okay, so this is what you mean when you say a random variable is a constant. So what's the expected value of x? Well, it's the values the random variable takes times the probability it takes them added up. So it's the sum of the values it takes times the probability that it takes those values added up over every possible case. But in this case, there's only one t sub I, which is the value c, and the probability is 1, so the answer is c. But of course, if I have a random variable that always takes the same value, then if I take the average of that random variable, it's got to be the same value. So nothing there. What about the variance? What's the variance of a constant going to be? Better be 0, because if the random variable doesn't vary, then something whose name is variance, if it produces some other result, then it doesn't make much sense as a definition. Remember that the variance is the average value of the square of the difference between the random variable and its average. And if the random variable always takes the average value, then the square of the difference is 0, so the average value of that should be 0. Okay, so let's see if we produce that. What's the expected value of x squared? Well, that's the sum of the ti squared times the probability x equals ti. Again, there's only one t sub I here, which is the value c, so that's c squared times 1, or in other words, it's c squared. So what's the variance? The variance of x from our formula is equal to the expected value of the square minus the square of the expected value. Instead of putting parentheses around here and putting the square out there, I use the convention that I put the square symbol right after the e. But people tend to get confused about that. Remember that later on in the course you're going to have to use this formula, and it's a common mistake for people to somehow or other confuse the average of the square and the square of the average with each other. They're not the same thing, except in this particular case. Because now, in this particular case, the average of the square, the second moment, we just calculated, it's c squared. The square of the average, there's the average, square it. So I have c squared minus c squared, of course, which is 0. Which is exactly what it should be. If a random variable is constant, its variance is 0. And you can go backwards. You could say that if a random variable has 0 variance, meaning it doesn't vary, then it must be a constant. This is actually in the book. Let's see. This statement right here. This is Theorem 4.1. I don't know why it has to be a theorem. Page 156. And this one here is also in the book. It's Theorem 4.4, which is on page 165. Okay, so this is all pretty simple-minded. Okay, let me erase this. Here's another example. We have so far, I guess I'll call that example 3. Or is it example 3? I don't remember what number it is. So to avoid that question, I'll just call it example. Okay, so the example, let's take the only other case that we know of, that specific case we've considered for a continuous random variable, where x is uniform, 0, 1. So we already calculated the expected value of x for that case. That was one of our previous examples. So what we did is we took the values the random variable takes, multiplied by its density function dt, integrated over all t. And if it's uniform, then this is the integral from 0 to 1 of t dt, because the density function for a uniform variable is 1 when t is between 0 and 1, and it's 0 everywhere else. This was an earlier example. And when you evaluate this, of course, the answer turns out to be 1/2, which is exactly what your intuition would tell you. All right, so what's the second moment? Same argument. I'm using the same thing right here. I take the values the random variable takes squared, because I want the average of the square. I multiply by the probability of taking that value, which is the density function dt. In other words, I'm just copying, well, let's see, I erased it here. So this is for mu. So this is this. Now, for the second moment, I take the integral of t squared. In this particular case, that's, again, the integral from 0 to 1, because between 0 and 1, this function is 1, but outside of that interval, this function is 0. So it's going to be the integral between 0 and 1 of t squared dt, which you can integrate. When you integrate that using the fundamental theorem of calculus, you get t cubed over 3 between 0 and 1, and that gives you the answer 1/3. So therefore, moving up here, the variance of x, if x is uniform 0, 1, from our formula is equal to the second moment, which is 1/3, minus the first moment squared. It's 1/3 minus 1/4, which is 1/12. Now, go back and look at homework 0. Because in homework 0, what you calculated for the uniform distribution was you calculated this and you calculated this. And so to get the variance, I just plug into the formula right here that takes the difference between these two, right there, so I get the answer. Okay, so homework 0. So again, this number has intuitive meaning. You would expect the variance of a constant to be 0. Here, a uniform variable, you'd expect the variance to be not 0, but whether it's 1/12 or 28, there's no reason for you to think one thing or the other at the moment. But later you'll see that intuitively that the more spread a random variable has, the bigger its variance is going to be. Okay, let's take another example. So this is also from homework 0. Okay, now I'm going to assume that x is exponential with parameter lambda. I haven't defined this yet, but in homework 0, I gave you two functions that were called density functions. Of course, then you didn't know what a density function was. One of them was the density function for the uniform, and the other was the density function for the exponential. So what this means is to say that the density function of x is given by 0 when t is negative, and lambda, which is a parameter, e to the minus lambda t when t is not negative. So in homework 0, this was just a function. Now, it's a probability density function, but you still don't know why you would pick that one over any other one. But you've already done some work on this. For example, you know how to draw its graph. So here is the density function of x evaluated at t. There's t. It's 0 when t is negative. And then, it, as a discontinuity, jumps up to the value lambda. And then it looks like that. So in fact, if you evaluated the integral, okay, I'll do it here. The integral from 0 to infinity of lambda e to the minus lambda t dt, that better turn out to be what? if I integrate a density function over the whole range of definition, I've left out the 0 because I've just been integrating over 0. What do I get? 1. So this better work. You can check that out, it's no big deal. That's the answer. Suppose I wanted to calculate the expected value of such a random variable. Now I got to keep emphasizing the next step in the course is to derive this, because this is supposed to be an important physical model, just like the density function or the uniform variable is an important physical model. This represents picking out a point at random in a finite interval. This is going to represent some other physical process that's going to be very important. But from one point of view, it doesn't matter what this is, because the stuff I'm talking about works for every possible function. It has the property that is never negative and its integral is 1. Those all could be density functions. Okay, so what's the expected value? Well, I use the expected value formula. I take the values the random variable takes times the density function, lambda e to the minus lambda t dt, and I integrate it over the whole range of definition between minus infinity and 0. That function that would fit in here is 0, and between 0 and infinity, it's what I said it is. So I'm really skipping a step here by not writing out the part with the 0 in here for the negative branch, because you don't have to keep writing zeros all the time. Okay, so what do you get? Well, you just evaluate that integral, and as you know from homework 0, if you integrate by parts, this turns out to be equal to 1 over lambda. So what this means is that when we figure out what this density function represents, whatever it represents, the parameter lambda that fits in there is the reciprocal of its average value. So lambda has a physical meaning. What's the expected value of the square of an exponential random variable? Well, same formula, 0 to infinity, but now instead of t, it's t squared. Lambda e to the minus lambda t dt. Again, homework 0, integrate by parts, and that turned out to be 2 over lambda squared. So that's the average of the square random variable whose density function is that. So what's the variance? The variance is equal to the difference between the second moment, 2 over lambda squared, and the first moment squared, 1 over lambda squared. And so the answer is 1 over lambda squared. Okay, so these are answers then that we're going to worry about later. That's the average of an exponential random variable in terms of its parameter lambda, and this is the variance of an exponential random variable. And in fact, this is done in the book on page 271. I guess if you'd had been smart enough to know that when you did homework 0, then you could have just gone to page 271 and referenced that. Okay, any questions here? All right. So now what I want to do is I want to consider a process for which it turns out that the density function that describes that random process is exponential. So this is going to turn out to be extremely important in terms of applications. This is going to take a while. I won't finish this today. But this is now, we're getting out of the rote stuff, and now we're looking at the stuff we have to understand what's going on. This is the essence of the course, because who cares about calculating these integrals or probabilities unless you know what they stand for? It doesn't mean anything. So what I want to talk about is what's called a Poisson process. Poisson. Named after a mathematician named Poisson. The big fish, as they sometimes say. Poisson is French for fish. Okay, Poisson process. Now the idea of a Poisson process is that I have something like, say, time or distance. Let's say time. So here's my time axis, and I have events that occur at random in time. So a typical example, which is the one that's always traditionally used in probability textbooks, is a Geiger counter. So a Geiger counter, you have this lump of material, and it's got these electrons or something in it, and the electrons decay at random. So every once in a while, you'll hear a click, and then another click, and then a click, and then a click, and another click, and so forth. And so the clicks seem to occur at random, and so the question is, this is a random process. Can I describe the randomness in this process? Now, there's lots of things that might fit the same model. That is, lots of things that might correspond to events occurring randomly in time. For example, you could take a stretch of I-95, and these could be the times at which accidents occur. Or you could take a season, and these could be the times at which hurricanes occur. In fact, anything you could think of in which there are random occurrences separated by, or occurrences separated by random lengths of time, could be a Poisson process. In order to be a Poisson process, though, we have to say something more than just the random events occurring in time, but I have to say something about how they occur in time. So I'm going to make the simplest possible model for events occurring in time. From the point of view of computer science and engineering, one of the major applications is that these instants represent the times at which messages occur, arrive at, let's say, a node for processing an internet. So what happens is, in the internet, you've got, or any kind of data communications network, you've got this stuff that zips around from node to node, and the instant at which one of these messages or pieces of data, whatever it is, arrives at a particular node is, for all practical purposes, random. And so if you're sitting there at a node, you might see these as the instant of arrival time of the message. And if you're an engineer who's designing or administering this kind of system, what you want to know is, how do I design a system in which the demands for the use of the system are random? That's the essence of it. And another example, computer science type example, is you can have, let's say, a CPU, some kind of operating system, and these are jobs arriving for whatever you do with jobs. So the jobs arrive, and they arrive at random, and typically if the server, the CPU, whatever it is that's handling these jobs is busy, then the jobs queue up. Just like in the internet, if the node is busy, then the messages queue up. And if the queue gets too long, then you have bad delays, and you can start dropping bits because the buffer size isn't large enough. And so the question that you want to answer is, how can I design a system to take into account the fact that it's designed to handle demands that are inherently random, inherently unpredictable, except in a probability sense. That's why you're taking this course. All right, so here's the model I'm going to make in order to describe this random process. Or, by the way, a Poisson process is a special case of what's called a stochastic process. And that's where the name of the course comes from. Stochastic just means random. And Poisson is a special kind of stochastic or random process. Okay, so the Poisson process is important just the way the uniform distribution is important. All right, so here's the way I'm going to describe it. I'm going to take my time, and I want to let x represent the times between arrows. So there's an x right there, and that would be an x. So this could be x1, x2, x3, and so on. So the x's represent the times between arrows, and the assumption is that they're all probabilistically or statistically identical. So we want to find the density function of the x. That is, how long do I have to wait from this click of the Geiger counter to the next click of the Geiger counter? How long do I have to wait from the arrival of a message to the arrival of the next message? That's part of the input to a more complicated problem of how you design systems that handle random demands. So the way I'm going to do it is I will take an interval, I'll call this 0, and I'll call this t. And what I want to calculate is the probability that x is greater than t. Now, the probability that x is greater than t is 1 minus the probability that x is less than or equal to t. That's the definition of distribution function. So what that means is that if I can calculate this distribution function, then I can calculate the density function and all of the stuff I need to know. But from the physics of the problem, to make this easier to do, instead of calculating the probability of less than, I'll calculate the probability of greater than and subtract from 1. Because it's just arbitrary that this was defined, the capital F is defined to be less than, it could have been defined to be greater than. That's just convention. So in this application, it's more simple. It's easier to worry about greater than. So the idea is that here's 0, here's t, and I want to calculate the probability that the time until the first arrow is longer than t. In other words, that the time in that x is greater than t. Okay, so the way I'm going to do that is this. I'm going to imagine, just like I did with the uniform, I'm going to imagine that time is divided up into little intervals, so time is discrete. And then I'm going to use the typical argument in physics and engineering, which is passed from discrete time to continuous time. So this will be interval number 1, and that's interval number 2, and this will be interval number n. And I'm going to calculate the probability that I have no arrival, no arrow in the first n intervals, and then I let n go to infinity, so that I pass from intervals to points, or from discrete time to continuous time. Of course, I'm going to do all this again next time. I'm just setting the stage because I don't have time to finish it, and this is very important. So what I'll say to start things off is I'll say, suppose little p is the probability that in one of these little intervals, because remember they're all identical, that I have an arrow. So if p is the probability of an arrow, 1 minus p is the probability of no arrow. And then I say this. The probability that x is greater than t is equal to the probability that there is no arrow here, and no arrow here, and no arrow here, and so forth. So what's the probability of no arrow in the first interval? Well, if p is the probability of an arrow, 1 minus p is the probability of no arrow. What's the probability of no arrow in the second interval? 1 minus p. What's the probability of no arrow in both intervals? Well, now I have to make an additional assumption. I have to assume that the intervals are independent of each other. In other words, if this is a Geiger counter, I'm assuming that the probability of a click here is the same as here, or here, or here, and that they are independent of each other. So that if I know that a click has occurred here, it doesn't give me any information about whether the next click is going to occur here, here, or here, or here. It's total randomness. So if it's total randomness, if each individual interval represents an independent trial for a click or not, or for the arrival of a message or not, whatever it is, then the probability of no arrow in these n intervals is 1 minus p times 1 minus p times 1 minus p, so forth, n times. 1 minus p to the nth power. So that's the independence assumption. This is the physical model. And then I take the limit of this as n goes to infinity. So in other words, I'm making my mesh finer and finer. Now, as n goes to infinity, what must happen? And I say I'm going to repeat all this next time, so I'm just running through it quickly. If n goes to infinity, then p must go to 0. Because if p is the probability of having a click in a little interval, if the interval goes to 0, then the probability of having a click at exactly that instant must go to 0 as well. Remember, the probability in a continuous random process of having an event occur at any specific value is 0. So n gets bigger and p gets smaller. But somehow or other I have to connect this to things I can measure. When I connect it to measurement, as I'll explain next time, this means the following. It means that the average number of arrows between 0 and t, if there are n intervals, is n times p. So as n gets bigger and p gets smaller, np remains constant. And that will be set equal to lambda t. Okay, so this is the important insight right here. And as I say, I'm going to discuss this again in detail. I want to let n get bigger, I want to let p get smaller, but I can't do this in an arbitrary way. It's got to be connected to what's actually happening. So the way I do this is I say, well, if p represents the fraction of intervals that have arrows, how many arrows would I expect to get on average in this interval? And the answer is, well, if I multiply the fraction of intervals, which is p, times the number of intervals, which is n, that will tell me on average how many arrows I'm going to get. Now, the average number of arrows I'm going to get has nothing to do with how I measure it, has nothing to do with how I draw my diagram. It's something that I would actually measure based on the Geiger counter or the particular process by which the messages are generated. So what I do is I set that theoretical value of n times p to lambda t. T is the time, and lambda is what I will call the rate. So if the arrows or the clicks occur at a certain rate, if I multiply the rate times the time, I would get the average number of arrows, which is the number of intervals times the fraction of intervals that have arrows. And I say I'm going to do all this next time, and then I take this limit. And when I take the limit, I get an answer, and we don't have any time, so I can't write down the answer. But next time I'll write down the answer. And explain where it comes from. Okay, any questions before we quit? Okay, see you next week.